Hey, good morning. We are going to talk about complex numbers on our first day because, wow, and just like everything, everything's not so complex once you understand it. All right, here we go. Yep, we're going to skip that. All right, so complex numbers. Last year in Algebra 2, you did quadratics and you got to a certain situation where you had square roots of negative numbers, and you're like, dang, a lot of people would be like, I'm good, walk away. But fortunately or unfortunately, some people got together and said, I think we can take it a little further. So they created a beautiful thing, and there's so much cool history about it, and I won't shy away from it too much. But right now, today, we're just kind of getting back into it. I is going to take the square root of -1. So if you had the square root of -16, you could rewrite that as the square root of 16 times the square root of -1. And we all know that that can be written as 4i. I will also throw out the idea that I squared is equal to -1. Anytime you see an I squared, you need to put a -1, or more importantly, you can put a -1 or an I squared wherever you see a -1. That's interesting. All right, so complex numbers have two parts, a real and imaginary. They get a little fancy notation, and you'll see this on IB World more than any other world. So it's important that you feel good about it. If we have 3 plus 4i as a beautiful complex number, you'll see that z, w, v, u are common variables for complex numbers. We'd say that, now I'm not that good at my cursive, but the real part of z would be 3, and the imaginary part of z would be 4. Well, that seems easy, because it is. What if w equals, let's say, 159? Is that a complex number? Well, it is. Remember, complex numbers hold everything. That's just a real number, but it can be written as 0i. So it's tricky things like that where we say the real part is 159 and the imaginary part of w would be 0, purely real. Can you have a number that's just I? Absolutely. If you had 7i, the real part would be 0 and the imaginary part would be 7. Not too tough. All right. The complex conjugate, super important. The way you're going to kind of get used to it because of how they multiply together. That's the key. A number and its complex conjugate. When you multiply them, what happens? And hopefully you walk out of here with a better idea with that. If I have z equal to 3 plus 4i, the complex conjugate, usually with that little asterisk, is just... So everybody thinks a complex conjugate has to have a negative. No. What if w equals 159 minus 7i? Its complex conjugate would be 159 plus 7i. All right. Notice the real parts always stay the same, and the imaginary parts just differ in sign. Cool. So that's how we kill people, I think, in mathematics, is we go and we kind of give you the just square this, multiply this. Let's remember that complex numbers is so much more. It is the life of so much mathematics, and that's why we think it's so important to teach you. But a lot of times we forget to teach you, like, in what direction. The Mandelbrot set is nothing more than a grid, and these are all complex numbers. Okay, like 5 plus 2i and all that. Each dot represents one of those complex numbers. And you do this little iteration to a dot, and then you decide what color it becomes. If you stay in the club, then you're just given a designation, in this case black, to be in here. But if you're right here and you decide to diverge to infinity in this little loop, then how fast you go away determines the color that you're given. So then everybody is designated at something. How good your pixelation is how fine that picture is. unbelievable math in here. There's Fibonacci numbers nestled in those bulbs, and just so cool. Fractals are amazing. Electricity, the language, the mathematical language of electricity is all complex numbers. But you're like, hey, there's no I in here. Well, what's funny is they turn the I into a J. There's a pay increase for sure. So be careful. A fun thing to do with seniors when we study some mathematics in abstract algebra, and I can't get away from that. We'll do a little of that, is how to multiply using regular polyhedron. And it's like all of a sudden you let the shape kind of create all these hard binary operations. So just by rotating this is taking a complex number and squaring it, cubing it, and so forth. So you get all these cool shapes. Computers, there was a contest who could create this flower, and the person who won it used complex numbers and created a nice little algorithm. Very simple too. Complex numbers are very simple. My favorite all-time equation is coming up. It is right there. And that bad boy is, it's just something to behold. Like you need like an hour just to stare at it. It's like a great painting. It's full of mystery and love and power and emotion. It's just, you go off in math and you study so hard, but then all of a sudden something so beautiful comes out of it, and it just doesn't seem real. But you actually have the tools to understand that and where that comes from this year. So we'll do that. All right, let's move on. So a historical note, I would say that complex numbers were kind of needed. The first time we have it is 50 AD. They came up with this. It's the correct mathematics. However, they see that it's not going to give them anything they can use on this particular pyramid, so they kind of leave it alone. Great. Well, 1,500 years later, oh boy, this thing likes to jump. Famous picture. This is in the last, 15 minutes, I've seen that picture and given 3 different names. Here, in the book, they say Bombelli. In another book, they say Cardano. And another book, they say Tartaglia. The same picture. Actually, kind of like a reflection of it. It is just crazy. But anyways, they came up and they say Raphael Bombelli is the first one to coin this. And that is 1,500 years later. And then this development, just think, if we didn't go there, would we be able to deal with some of the things that we deal with now? Electricity, fractals, just so much cool stuff with fractals. So back to your world. What are you going to be asked to do? You're going to be asked to, how do you see it? How do you write with it? How do you get used to it? So we're used to the square root of 16 as 4. This is not plus or minus 4. The sign is already given here. If you take the square root, that's when you have to do plus or minus. But if you start with the square root, it's whatever sign's in front. Here, like I did earlier, is the same thing as the square root of 16, square root of known what. So you're kind of factoring that I out, and here you would have 4i. Square root of 7, oh my gosh, just leave it as square root of 7. Don't put that in your calculator and get further away from the truth. Just leave it like that. But the reason I put that here is this is the square root of 7, square root of -1. So we'd write square root of 7i. A lot of people get nervous about that I being behind it because it's like, is it under the square root? So a lot of people will write it I times the square root of 7. Very good. So some of our first examples, this is where you would take the square root. So you're like that. I'm not going to show every step like this because we don't have time, but certainly this is what's behind. When I would hope that you go from x squared -4 right to plus or minus 2i. Hey, quadratic formula is kind of the reason we got this really cool way of solving quadratics. We thought it always works, but sometimes it doesn't cross the x-axis. Therefore, our discriminant the b squared minus 4ac in the quadratic formula is going to be negative. I know I'm talking fast like a math teacher, like everybody understands me. So that solves the quadratic. It gives me roots. And sometimes there are no roots. It doesn't cross the x-axis. So we get what we call complex numbers, and we say no real solutions. That doesn't mean there's not complex number solutions. So if we plug this in, we get -1 plus or minus the square root of 1 squared minus 4 times 1 times 2 over 2 times 1. The reason I write this is when I just write it and then I do the video, I go way too fast. So hopefully 1 minus 8 is -7 over 2. And so we get -1/2 plus or minus I times the square root of 7 over 2. That's weird. Why don't I leave it just like that? I can. But when we get used to complex numbers, it's really important to kind of recognize what's the real part and what's the imaginary part. So there are two values that I could plug in for x into that original quadratic and it would work. I'm not going to ask you to do that right now. All right, sum of two squares factorization. This is skill work, 100%. How do you get good at skill work? You don't listen to me tell you on a video this is how you do it. You do it. It's like saying hola in Spanish. You don't just read it and see somebody say it and go, okay, I got it. You got to say it because it comes out weird the first couple times. So the sum of two squares. All right, well, kind of a review, and to even know why I would even talk about this is what if we had a squared minus b squared? This is something that needs to be automatic. It's probably not automatic after 7 months, but you need to know that that has to be factored. And the way math books work, the way we teach math, is we use a lot of situations that can be factored. In reality, that's not true, but we have to kind of play the game here, and the game is to recognize things. So what if I had x squared minus 16? Well, that's difference of squares, x plus 4, x minus 4. Oh, Mr. Sayers, you always pick these really hard examples that nobody can understand. Yeah, what if x squared minus 7? Well, I can't do that because there's no number times itself gives you 7. Or is there? All you're doing is taking the square root of 16. That's why it makes it easy. Well, what's the square root of 7? Square root of 7. So don't be scared. Don't be scared. All right, final example, x to the, let's go 26 minus 5. Is that a difference of squares? You bet. The square root of x to the 26 is x to the 13th plus the square root of 5, and x to the 13th minus the square root of 5. You don't believe me? Multiply those out. You get x to the 26 minus 5. So please open your hearts and souls to recognizing that you can take the square root of both sides. All right, so here is the sum of squares. Now the sum of squares can be factored in basically the same way, but all of a sudden we have to employ the -1 or I. And the way that works is a squared plus b squared is the same thing as a squared minus a -1 times b squared. That's dumb, right? Nobody does. Why would you add two negatives instead of a positive? Well, it's not too dumb because in place of that, I can put that as I squared b squared. Now we have a difference of squares. So now we can write this as a plus IB, and a minus IB. It's usually written BI, but you know, you throw in IB where you can. I guess it is applicable. Okay, all right. So write as a product of linear factors. So most time people just don't understand the question. That means factor this sum of squares. So that's going to be x plus 2i, x minus 2i. and oh, Mr. Sayers, I don't know, x plus square root of 11 I and x minus square root of 11I. See how that I kind of floats there and you don't know? So you probably in the back of the book are going to see it as, very good. I know I'm flying. In order to get this, you're just sitting there. I hit pause, get a piece of paper out, and start writing some of these down, and just mimic it for a little bit. You're going to have to say "Ola" a couple million times before it just rolls off your tongue. So just like the mathematics, you're going to have to say it. You're going to have to read it and write it, and so you recognize it when you need to. All right. I'm not a big fan. The only reason I can bring these up is because I don't agree with how they solve it. This is how the book solves this problem. I just don't want you to see it in the book and get confused about what do I want. I want you to do the easiest method, the most efficient. But the book says, hey, I recognize this as x squared minus 9I squared. Okay, that negative negative. So that's x plus 3I, x minus 3I. And that's going to be x is equal to negative 3I and x is positive 3I. That's pretty cool. Wow. You bring in an I squared, you're using difference of sums. That's pretty fancy. Or why don't you just write x squared equals negative 9, x equals plus or minus square root of negative 9, x equals plus or minus 3I. I would hope that you get very quick at something like this and go for it. If you want to try this one, you can pause it, boom, and we're back. Hopefully you got plus or minus the square root of 3/2, and then I can go way out here, or we'll sneak it in there. All right. So we dice it. We get a little bit more interesting. And I'm just trying to do as many examples as I can so you kind of get back into it. I'm going to factor out an x. And you should recognize difference of squares right away. Right away. Give yourself some time, but try to recognize it. How about that? X plus 2, x minus 2, and we get x equal to 0, negative 2, and 2. Cool. Might be the curves of something. That might be the max and mins. We did a lot of cool calculus last year. So we factor out an x on this one. It's not difference of squares, so don't be scared. But we have this new tool that we can write this like that. And so here we'd say 0, negative 2I, and 2I. Go ahead, plug them in. You will get 0. It will work. All right. So now we're into the homework a little bit, and all of a sudden things changed. It's not like the little examples Mr. Sayers did. So let's do one of these real quick. X to the 4th plus 2x squared minus 3 equal to 0. Hey, this is a tough one, even if we're just doing quadratics, because it's kind of a disguised quadratic. I noticed that x to the 4th, it's a perfect square, so I'm going to try to factor it. And I will tell you on these, most of them are factorable. X squared, two things that multiply to give you negative 3 that combined to positive 2 would be plus 3 minus 1. I think that works. Yep. So now we have two different problems to solve. That's the zero product rule. I'll do the tough one. X squared equals 1, x equals plus or minus 1. Here we get x squared equal to negative 3, and x is equal to plus or minus I times the square root of 3. All right, this is a little bit awkward. I know, you haven't done it for a while, but hopefully you're giving yourself that ability. When you see that negative, you're taking the square root, it basically you make sure there's an I in there. All right, operations with complex numbers. Hey, can we add them? Can we subtract them? Can we multiply them? And most importantly, can we divide them? And the answer is yes, and it's so you have it. The intuition is there, it's correct. When you add them, you combine the real parts and you combine the imaginary parts. That's it. I'll give you a quick example, but nothing's changed. When you multiply, yes, you distribute and you combine like terms. So nothing changes with addition, subtraction, and multiplication. Division, on the other hand, is a little awkward, a little new. I'm not too sure how much you did this last year, but you know, let's do a quick little example. All right, if z and w, if you want z plus w, you're going to get 4 plus 2i. Hopefully you can see that I'm combining the 3 and the 1 and the negative 2 and the 4. If I do z minus w, 3 minus 1 is 2, and negative 2 minus 4 is negative 6. That shouldn't be too tough. If I write zw, then it's going to be 3 plus 12i minus 2i minus 8i. Sorry, I'm not that good at it. Oh, minus 8i squared. And I have to kind of show all my steps. So that's going to be 3 plus 10i. Remember I squared? This is always equal to negative 1. So that's going to give me a plus 8. And finally, I get 11 plus 10i. Awesome. All right, let's talk about division. So when you take a complex number and you divide it by a complex number, you want a complex number. So the critical move, and I want you to write that down, is you multiply by a very fancy one. Fancy one. All right. So that needs to go away. All right. So what's the idea there? Well, we didn't really talk about it, but do you see that this right here is what happens when you multiply a plus b times a minus b? Well, you get a squared minus b squared. Well, in the bottom there, I'm going to get c squared minus d squared. In other words, the I is going to go away. So that's the critical move right there. So when you multiply this all out, you get this. That doesn't mean I don't like this. I don't think that this is like important. That's what happens when you multiply. It's not a formula. Don't think of it as a formula. Think of it as a step, and if you perform that step, then you are good to go. So let's do a real life example. Let's go with 3 plus 4i over, 5 minus 2i. Okay, when we see that division, we're like, dang, we don't care about the 3 plus 4i at all. It's all about looking at the denominator and making that work. So we're going to multiply by 5 plus 2i over 5 plus 2i. Let's see what happens. On the top, I get 15 plus 6i plus 20i plus 8i squared. And on the bottom, I get 25 plus 10i minus 10i minus 4i squared. All right. Hey, some people just need to multiply this out a couple, 20, 30, 50, whatever, until they recognize that, you know what, those middle terms are always going to go away when you have these opposite signs in there. So you do what you need to do. The I squareds are negative 1. So when we combine 15 minus 8, we get 7 plus 26i over 25. Careful with your negatives. Negative 4, negative 1, positive 4, I get 29. If you want to rewrite this as a real part and imaginary part, 7 over 29 plus 26i over 29. That's it. That's supposedly easier. That's a new number. It is one complex number made out of the quotient of 2. So doable. Hey, this is out of your book, so I'm not going to show you. It's what you expect. Maybe you practice it real quick. 3 plus 2i and 4 minus I. Check it out. I think that would be good for you. Maybe you went and did that. All right, here are your solutions. Yep, that's not surprising. That's surprising when you mess up your negatives. When you multiply them. Oh boy, it's frozen. All right, new battery. Let's see if it works. All right. If you did that correctly, life is good. So you are multiplying by the complex conjugate of the denominator. You multiply it out, and look at that. Sure enough, 16 plus 1. 16 plus 1 is 17. So the faster you look at those and see 16 plus 1, life's good. Hopefully that worked out for you. Hey, I'm not going to do these problems. I'm just going to start you. I would choose to multiply by top and bottom. 1 plus 2i, and then 3 plus 2i over 3 plus 2i. Hey, I know on the bottom I'm going to get 9 plus 4, so I'm done there. Hey, whatever happens on the top happens. You're going to multiply this maybe first, or maybe you do the 2 minus I, 3 plus 2i, doesn't matter. Hey, last one. This is off your homework, so I thought I'd get you started. It's a little bit awkward, like in the form a plus bi, we don't know really, we got these different numbers. That's exactly what they are. They're just different numbers. So perform the division first. And that means multiply square root of 2 plus I, square root of 2 plus I, and just get this done, and then add 1 to it. That's it. So on the bottom, I will tell you square root of 2 times square root of 2 is 2, and we get that plus 1. So I will let you take it from there. Thank you very much. Toodaloo.